Today, it's all about plant nutrition. I know, plants need nutrition too, right? So in addition to water, the plant roots, they'll absorb all kinds of nutrients that the plants need. Now, to be clear, plants, they don't have any essential organic molecules. They have no essential vitamins or amino acids or lipids or fats. And fats are lipids, by the way, if you remember. They make every organic molecule they need, every single one. That's really different than you and I. We have these essential amino acids, things that we need, but we can't make. But not plants. They can make all of the organic material. And when I say that plants can make other organic molecules, we're talking nucleic acids, amino acids, carbohydrates, lipids, pigments, signaling molecules, you name it, they can make it. And they make it from very small molecules as well. Now, plants require nutrients from the soil in addition to water and carbon dioxide. Now, plants, they require some nutrients, things like nitrogen, phosphorus, potassium, sulfur, magnesium, iron, calcium, and a few other small nutrients from the soil. And of course, they're absorbing these through their roots. And from these molecules, carbon dioxide, water, nitrogen, phosphates, you name it, they make everything they need. And, we've known this for a really long time, going all the way back to the 1600s, like 400 years ago, right? This guy named Van Helmont, what he did is he measured out the mass of some soil, and then he grew a tree in it for years. And he carefully measured, the mass of the soil, how much water he added, and then at the end of his experiment, he measured the tree. And he realized that over 5 years, the soil only lost like 60 grams. That's it. Everything else came from water and carbon dioxide. It's kind of weird to think about this, but trees almost grow by pulling stuff out of the atmosphere, in this case carbon dioxide, and water from their roots. But all the carbon in a plant and in you was fixed by a plant from carbon dioxide. So, what is an essential nutrient? Now, I want to be clear. There are essential vitamins, like vitamin C, that you and I can't make. There are essential amino acids, the 8 or 9 amino acids that we need but we can't make. Those are organic molecules. Plants have no essential organic molecules, things they need that they can't make. They can synthesize, they can make everything they need, but they do have essential nutrients. And these are nutrients that include elements, right? Like nitrogen, phosphorus, potassium, magnesium, sulfur, calcium, right? These are elements that might be in the form of molecular ions like phosphates or nitrates, but they can't make these things. And we know this, right? Elements, you can't change an element through a chemical reaction. Only a nuclear reaction can change an element. So we have micronutrients, things that plants need in very small amounts, like magnesium, right? They need small amounts of magnesium and iron, and they need magnesium for chlorophyll, actually. And then there's the macronutrients. Macro means large, and these are what the plants need in large amounts, and those, of course, include hydrogen, carbon, and oxygen, and we know where they get most of that from. Of course, carbon dioxide and water. And plants get all of their carbon from carbon dioxide. Unless you're a parasitic plant or a carnivorous plant. In that case, it's a little bit different. So carbon dioxide and water supply basically hydrogen, carbon, and oxygen. And that's 96% the mass of a plant right there. And another macronutrient is nitrogen. And in fact, I usually always say hydrogen, carbon, nitrogen, and oxygen is like 96% of what we are. So nitrogen is a primary macronutrient. Even though our atmosphere is well over 70% nitrogen as a gas, and two, it's not very available to plants, so they have to use bacteria or other ways of getting nitrogen. And they get most of their nitrogen in the form of nitrates, NO3 minus. Okay, so that's an anion, but it's a molecular anion because NO3, they're held together. The nitrogen and the oxygen, they're held together by covalent bonds. So we have a molecule, okay? But since it's charged, it's an anion because it's got a negative charge. And then you need nitrogen for all kinds of things. You need nitrogen to make amino acids. You need nitrogen for your DNA. And nitrogen is also important for making chlorophyll. So what happens is if you have a nitrogen deficiency, the plants often don't grow well because they can't make the chlorophyll they need. And the plants will become what we call chlorotic. And a chlorotic plant, have you ever seen leaves that look yellowish, especially in the outsides of the veins? So you got the veins that look all nice and green, but outside, that chlorotic look, that yellowish look, means they cannot make the chlorophyll needed to capture sunlight. And of course, if you don't have chlorophyll, you're not doing as much photosynthesis, you're not producing as much carbohydrates. Guess what? You don't grow very well. Another macronutrient, phosphorus. Once again, this is important for making ATP, adenosine triphosphate. You need phosphates also for the sugar phosphate backbone of your nucleic acids to make DNA. And of course, they don't absorb phosphorus as elemental phosphorus. They absorb it as phosphoric acid, which is H2PO4 minus. And phosphates are often quite limiting. And, it's hard to identify a phosphate deficiency at times. Another macronutrient, potassium. Now, potassium is an electrolyte. Now, unlike nitrogen and phosphorus, this is actually an electrolyte. It comes in as a elemental ion and is positively charged because it loses an electron, right? So potassium is used for a lot of different things in plants. It's used to help maintain water balance. You need potassium to open and close the stomata, and it helps with other various metabolic processes. And of course, potassium, like our other nutrients, are taken up by the roots. Now, secondary macronutrients include calcium, sulfur, and magnesium. So for instance, magnesium is used to make chlorophyll. Now, plants extract their nutrients from the soils, okay? So you can imagine that the property of the soil is going to affect how the plant extracts the nutrients. Now, as a first pass, soils come from rock weathering, and that creates much of the soils we see today. Now, soils do have an organic component from the breakdown of, organic material, plants and animals, but in general, our soils come from rock weathering. Now, soil has, since it comes from rocks, there's different textures of soils. And of course, different types of rocks are going to create different types of soils. But basically, we can identify soils on different sizes, from gravel, which is, greater than 2 millimeters, to sand, which is very coarse. Sand also is not going to hold water very well. It's very porous. To silt, which is a bit smaller than sand, which will hold water better, all the way down to the finest particles, which are clay particles. And clay particles can actually hold on to water so tightly that you could have it full of water, but the plants can't extract the water from the clay. So, soil texture and pH are two properties of the soil that affect how the plant's going to extract nutrients from it. So the soil texture, that's going to depend on the amount of sand, silt, clay, and the amount of organic matter you have mixed in with this. So soils can be incredibly varied. Now, the importance of soil textures, if you have very hard clay, like where I live, I literally took a pickaxe to help me dig a hole because I was bending my shovel on it because the clay was packed in there so tight. Now, you can imagine what that's going to do for root penetration. In that case, it's going to be really hard for plants to send their roots through this very compact clay. On the other side, if you have sand, it's really easy to grow through sand. But one thing is, when it rains in sand, hey, water is very easy to extract, but then it's going to dry out quickly because sand is very porous. On the flip side, your clay might have lots of water in it, but the water molecules are held very tightly to the clay. And then as a result, that water might not be very available to you. Going back to sand. Sand is very porous. Lots of oxygen, no problem. Whereas if you have a lot of organic material and it's wet all the time, well, you might not have a lot of oxygen because the oxygen is being used to break down the organic material. If you have compact clay full of water, you may have low oxygen availability. Now don't forget, we always talk about plants producing oxygen, but the roots, they need oxygen. Plants are eukaryotes. They have mitochondria. They rely on cellular respiration just like us. They just do it at a much slower rate than we do. Now, pH has a huge effect on nutrient availability. Now remember, pH is a potential of hydrogens. What it's saying is how much hydrogen ions you have, or hydroxide ions. And it's a log scale of 10. So if I go from a pH of 7, which is neutral, which means I have the same amount of hydrogen ions and hydroxide ions, they're equal concentrations. If I go from pH 7 to pH 6, it means that I have 10 times the amount of hydrogen ions, which are basically protons. If I go from 7 to 5, I have 100 times more hydrogen ions, protons. And you can go the other way. If I go from a pH of 7 to 8, I'm becoming more alkaline, more basic. Your hydrogen ion concentration goes down, but your hydroxide ion concentration goes up. Now this is important for several reasons. One, ions are reactive. Remember, chemical reactions rely on making and breaking chemical bonds. They're often involved with sharing electrons. So if I have lots of ions, well, they're chemically reactive. They're going to affect our molecules by forming new bonds. Also, did you remember calcium, potassium, nitrate, phosphate, and chloride ions? These are all ions. So if I've got ions, right, that I need, my electrolytes, then pH is going to clearly affect their availability as well. And plants need ions. They need electrolytes. So soil pH is going to affect their availability. And we have these elemental ions like potassium and chloride, and we have molecular ions, which are the phosphates and the nitrates. So anions are negatively charged. These include chloride ions, phosphate, and nitrate. And remember now, phosphates and nitrates, these are some of the most limiting nutrients that plants might face, but yet they're macronutrients as well. And they're easily available to most plants, and they interact with water easily through hydrogen bonding. Now that's important, right? So, hey, they're easy for the plant to get because they're going to dissolve in water. However, if you have too much watering, you can actually leach away your nutrients. And in fact, when you clear cut a forest, you might lose your nitrates. And in fact, that's what they've discovered in large experiments where they've done small scale clear cutting. They've realized that nitrogen is quickly washed away from those soils. And that makes it harder for plants to grow there. So if you clear cut your forest, there's less nitrogen, plants can't grow. So it takes a lot longer to rebuild your forest. So that's important. The next ones are the cations. Now cations are positively charged. Potassium, calcium, magnesium. Now they are often attracted to negatively charged clay particles. So that means they might be in your soils, but if you've got a lot of clay, then it might be hard for the plants to extract them. We'll talk about that later, how the plant gets them through cation exchange. So as you can see, soil pH matters. And you have, of course, different soils with different pHs. And as you can imagine, there are different plants adapted to different types of soils. So coniferous forest, they often have acidic soils. You've got carbonic acid, phosphoric acid, nitric acids that can build up in these soils. So you have plants that are adapted to extracting nutrients in these soils. Alkaline soils. You have your cations, calcium, magnesium, sodium, potassium, and they might be forming as carbonates or different types of salts. So in alkaline soils, calcium carbonate might be abundant. And then your calcium ions replace your protons and you get bicarbonate. And that affects, what the soils are, what's available to the plants. So basically, most plants like around a neutral pH to slightly acidic, 6 to 7. There are exceptions. There's a plant called rosemary. Rosemary is a great herb. And I love the smell and taste of rosemary. Rosemary biscuits are awesome. Rosemary wheat crust on a pizza is pretty good too. But they like alkaline soils with a pH above 8. Whereas a blueberry, they might like more acidic soils, like a pH of 3 to 5, which is getting pretty acidic. So if you've got cations and you've got clay soils, then they're going to be easily bound to that. And your anions, they're not going to bind to the soil so much. They're going to remain in solution. So we have different problems associated with each of these. So if you have low pH, what that does, low pH, more protons. If you've got cations attaching to the negatively charged clay particles, but if you lower your pH, that's going to knock those cations, sodium and potassium and calcium, off of those soil particles, and it can cause them to either be leached away or, guess what? So if you're a plant and your cations are bound to your clay particles, one way you can knock them off is to pump protons into the area around your roots. Is this another proton pump? It is. You pump protons into the soil, you lower the pH, the protons knock the other cations off. Guess what? You can now uptake them through the roots. So that's one way that plants can exchange their nutrients. So in my next lectures, what I'll talk about is the adaptations plants have for these nutrient uptake, and we'll also talk some about the symbiotic relationships of plants as well. All right, this has been Tom Kennedy's Science.